Good morning, everyone. I am Preet Sharma, and today I will be explaining Routh Hurwitz stability criteria, which is a very important technique to use in control system, which finds the stability of the control system without using any complex equations. So let's start with the first slide. What is stability? In control system, stability is very important. As for example, let's take an example of a scooty, where the accelerator is a control system, where if we increase the acceleration, the speed of the scooty will increase. But if the system is not stable, then when we increase the acceleration, the speed may or may not increase, which will be very dangerous for our rider. Similarly, let's see what stability criteria we are going to study today. And the stability also is dependent on how the output is changing with the input. If the input is bounded and the output is not bounded, then the stability of the system will not be very good, or we can say it will be unstable. And why it matters, as here we can see the example motor speed control that I have given, and this is the bounded input I was talking about. And here we can see the input is bounded and it is not tending to infinity at any point. Similarly, the output is also bounded and it is not tending to infinity. So this system can be said to be stable. Let's move to the next slide. Types of stability. We have three types of stability in our instability. The first is stable, second is unstable, and third is marginally stable. So these are typically dependent on the location of the poles. So let's consider a graph like this. Here, let's take the x-axis as real axis and y-axis as imaginary axis. And if the poles, all the poles of the characteristic equation are on the left hand side of the imaginary axis, then it will be stable. If any of the poles, as written here, if any of the poles is on the right hand side of the imaginary axis, then it will be unstable. And lastly, marginally stable. Here, if any of the poles or all the poles are on the imaginary axis, then it is said to be marginally stable. We would, or we are most likely to consider our system to be stable, or we want our system to be stable. So how to find if our system is stable or unstable? We use Hurwitz criteria. For that, we use characteristic equation. Now, what is characteristic equation? For example, if there is a transfer function and we find the transfer function through the equation of, if suppose there is g of s and unity feedback is uh, placed there, then we get the transfer function as g of s divided by 1 plus g of s, where the numerator will be our characteristic equation. Similarly, consider this some kind of characteristic equation. This is general characteristic equation, and we have to find if this system is stable or not. So for this, we use Routh Hurwitz criteria. Its purpose is to determine the system stability without computing actual poles locations. So we don't have to actually find the locations of the pole on the graph. So, and here we construct a matrix type structure, or we can say row and column type structure. And we can find the stability by checking the first column of the Routh Hurwitz matrix, and if there are no sign changes in the first column, then the system is stable. But if there are sign changes, like from 3 to -2, there is a sign change, so it will be unstable. Root information of sign changes equals that's okay. Let's move to the constructing the Routh array. This is the array I was talking about, in which we place all the values. Like you can see here, the maximum power of s in Laplace domain is n, so we plot that here, and then we, in decreasing order, we plot all the powers of s till s to the power 0, and we put all the values of coefficients of like this an minus 1. So we put in the first row an minus 2, leaving 1 and putting all the similar powers like even powers and odd powers like that. So for example, here we have put it an, then an minus 2, then an minus 4. Similarly, remaining up placed here like an minus 1, an minus 3, an minus 5. To calculate the further rows, we can use this formula. To find b1, we will multiply an minus 1 and an minus 2 and subtract an into an minus 3 and divided by an minus 1, so we get b1. For b2, we can do an minus 1 into an minus 4. Similarly, an into an minus 3 and divided by an minus 2, we can get b2. And we have to fill the whole table till k and check the first column. If there are any sign changes, then we can say that the system is unstable. But if there is no sign change, then we can say the system is stable. Let's move to the next slide. This is an example where we have taken the Routh array, and we can see the first row has no sign changes, so it is a stable system. And the conclusion we can come out with is that our control system here is stable. There are two special cases in our Routh array. First is if there is any 0 in the first column. Consider, let's take there is a 0 here. Then if you try to find C1 here, and we have to multiply this and this to like 0 into 3 and minus 1 into 4 divided by 0. If we divide by 0, we get infinity, and we don't want any infinities in our table. So we replace our 0 here, as you can see here. So we can replace our 0 with a very small positive number epsilon and solve our equation further. And after solving, we can put instead of epsilon, we can put limit epsilon is tend to 0 to solve our Routh array and find the desired sign changes. Another special case is an entire row is 0. Consider like our entire row is 0. So we form auxiliary polynomial. Wait a second. Auxiliary polynomial where we will form this. It is like a little bit complex, so we will not discuss about it, but this is another special case. So our key takeaways are we can use Routh stability criteria to find stability of the control system, so it is efficient in finding the stability test. It does not require any complex calculations, and we can find the stability of our system without finding the locations of our roots or poles. So that's it. Thank you.